Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video, we're going to review carbonyl substitutions and additions in a single slide. A carbonyl is a functional group featuring a carbon-oxygen double bond, and the primary feature of the carbonyl group is the electrophilic carbonyl carbon. The carbonyl carbon is partially positive due to both resonance of the carbon-oxygen double bond and the electronegativity difference between the carbon and the oxygen. As an electrophile, that carbon is a site of nucleophilic attack. Carbonyls can be broken into two categories, those with a good leaving group. These are also known as the carboxylic acid derivatives, and we generically represent the good leaving group with a Z. And those without a good leaving group, which are aldehydes and ketones. If a carbonyl has a good leaving group, the primary reaction it will undergo is substitution, and if the attacking nucleophile is strong enough, the resulting substitution product will also undergo an addition. If a carbonyl does not have a good leaving group, the primary reaction it will undergo is an addition. Carbonyls also have an acidic alpha hydrogen. However, reactivity at the alpha carbon is not covered here. The substitution followed by addition mechanism is crucial to organic chemistry, especially because so many reactions involving carbonyls are simply going to follow this same pattern. So it's very important that you understand the substitution and the addition mechanism because they come up so frequently. It's so important that I actually call this mechanism the most important mechanism for Organic Chemistry 2 students. So let's review this entire reaction mechanism. We're starting out with a carbonyl with a good leaving group Z, and we're going to react it with a strong generic nucleophile as shown here. As usual, we're going to draw an arrow from the negative charge to the positive charge. So in other words, from the lone pair on the nucleophile to the electrophilic carbonyl carbon. That, of course, is going to create a new bond between the carbon and whatever that nucleophile was. And since carbon can't have 5 bonds, we're going to take this pi bond to the oxygen. We're going to take those 2 electrons and move them up to the oxygen. That gives us the intermediate shown here. Now, we know this is a substitution because we had a good leaving group. So what happens next is the lone pair comes back down from the oxygen and recreates the double bond. In turn, that is going to kick off the leaving group Z. This gives us our substitution product, another carbonyl. Now, the difficulty in studying carbonyl chemistry is not actually the mechanism itself. As you can see, this substitution mechanism is pretty straightforward and is only 2 steps. The difficulty lies in knowing all of the reactants, whether they will do a substitution and an addition, a substitution only, or will only do an addition. While covering all the reactants is outside the scope of this video, it is covered in other videos. For now, we're going to assume that that nucleophile was in fact strong enough to do both a substitution and an addition. So that means that we're not done with this substitution step. We're going to follow it up with an addition. We're going to take that carbonyl product from the substitution, and we're simply going to react another equivalent of that strong nucleophile with it. The nucleophile that we substituted in is not going to be a good leaving group, so now we can take that nucleophile and attack the electrophilic carbonyl carbon to initiate an addition reaction. And this step looks very much like the one above. We're going to draw an arrow from the lone pair on the nucleophile to the electrophilic carbonyl carbon, and that's going to send that pi bond up to the oxygen. Once again, the intermediate is shown here. However, this is not a substitution, and there's no good leaving group to kick off. That's why we need a source of hydrogen in the next step, such as water. And what's going to happen in the second step in addition is that the negatively charged oxygen is going to attack the hydrogen, giving us an alcohol product. It is very common for students when they're first learning this mechanism, both the substitution and the addition parts, to try to protonate too early instead of doing a substitution and kicking off the leaving group, or to try to bring that lone pair back down to create a double bond. And again, for the substitution, it comes back down and kicks off the leaving group because carbon needs to have 4 bonds. But for the addition, you can't bring it back down because that would create a 5th bond on that carbonyl carbon. As a final note, before you start drawing, it's very important that you map out what you know about the carbonyl and the nucleophile it is reacting with. By doing so, you'll minimize the likelihood of making a mistake. For more information on this, check out the video, The Organic Chemistry Reactions Problem-Solving Process. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.